Hello everyone, welcome to the second lecture. In this lecture, we are going to talk about binary numbers which are used in our computers. It is well known that every computer is working with zeros and ones. But what are these zeros and ones? They are referred to as binary numbers. But what is binary and why do computers use them? How do computers convert all the information being images, music, numbers, etc. to zeros and ones? Binary is simply a system of counting. Before we introduce binary, let's talk about other systems of counting that were used before binary system. So we have here tally mark system and based and positional. Based and positional is the usual counting we use every day, and tally marks is a historical system that was used before the numbers were invented. In tally mark system, we work with marks. We put a mark for every object that we want to count. For example, you see here we want to count 4 objects, so we put 4 marks. So we will have as many marks as the number of objects that we want to count. So it is obvious that this system is not efficient in terms of the number of digits that it has to use. Consider each mark as a digit. In based and positional or the decimal system, we have different symbols rather than tally mark system, which had only just one symbol. Here we have different digits, different symbols, which are basically 0 to 9. And you see here that we can count up to 9 objects just using 1 digits. So it is obvious that it is much more efficient than tally mark system. In based and positional, we add a new digit every 10 things. So each digit that we have exponentially increases the number of things that we can represent. So with 1 digit, we just can count from 0 to 9, which is 10 numbers. When we add when we add another digit, we can count 100 things, and then we can count 1,000 things. So each time we add a new digit, it is multiplied by 10. So let's see how the digits, what is the power of different digits in based and system. So here you see a decimal number in the first row, which is green. So each digit in this number has a different power. For example, the first digit, which is here 6, shows the number of ones, or 10 to the 0. The next digit shows the number of tens that we have in this number. The next one shows the number of hundreds and the thousands and 10,000s and so on and so forth. So here you see that although we have the same digit used in these two positions, but they don't have the same value. One is showing the number of thousands and the other one is showing the number of 10,000s. This is what is used also in other counting systems. Here we are using base 10, but we can have other bases as well, which is what we are going to discuss today. So in base 10, each time we go beyond 9, we add a new digit because our digits are only from 0 to 9. In binary system, each time we go beyond 1, we add a new digit. So each digit goes basically from 0 to 1. So in this case, in this system, we have only 2 digits, 0 and 1. So let's see how we can count in binary system. 0 is, so in the left-hand side, I have written decimal numbers, and in the right-hand side, they're equivalent binary numbers. Here is a quick review. I will show you in more detail how we calculate the binary representation of a decimal number. So 0 is simply represented by 0, 1 is represented by 1 in binary. These two below here shows that we are using base 2 system or binary system. So binary is base 2 and decimal numbers are base 10. And 2 is represented in binary system as 1, 0. 3 is 1, 1. Because in the first position, we are counting the number of ones. And in the second position, we are counting the number of twos. And in the next one, we are counting the number of fours and so on and so forth. Everyone is a power of 2. So 4 is represented like this and so on and so forth. So you see that here for showing 7 objects, we need 3 digits in binary number, but in the decimal number or base 10, we need just 1 digit. So in binary system, each additional digit that we add, we increases the power of 2. In base 10 system, our digits are from 0 to 9. So each time we want to go from we want to go beyond 9, we have to add a new digit. In binary system, we are simply using base 2. So our digits go from 0 to 1. So each time we want to go beyond 1, we add a new digit. Let's see how counting works in binary system. I will explain later on more in more detail how we convert numbers from base 10 to base 2 or binary, but here is a quick review. So 0 is represented by 0 in binary system. This 2 here means that we are using binary or base 2. And in the left-hand side, we have decimal numbers. So 1 is again represented by 1, but 2 is not represented by 2 here because here we have just 0 or 1. So we put 0 in the first place and we put 1 in the second place. That counts the number of 2s. And you see here, for example, when we want to count 4, we need 3 digits here because the first one is the number of the 1s, the second one is the number of 2s, and the third one is the number of 4s. So we have 1, 0, 0. And it is interesting to see that although we could show 7 objects with just 1 digit in decimal system, in the binary system, we need 3 digits. So you see, we need more digits in binary system to show the same number that was showed in decimal number. In binary system, each additional digit that we have, it shows an increase in the power of 2. So remember in base 10, we started with 10 to the 0, 10 to the 1, 10 to the 2, and so on. Here we have 2 to the 0, 2 to the 1, 2 to the 2, and so on and so forth. So this basically means that in the first position, we are showing the number of 1s. In the next position, we show the number of 2s and the number of 4s and the number of 8s and so on and so forth. So for example, here, this 1 is showing that in the number we want to represent here, we have 8. But this other one means that in this number, we have 1. So it's basically an odd number. So if we want to calculate to see what is the decimal representation of this number, we need to know what is the value for each of these positions. So here we have 16, and then we have 8 in here. These are 0, so they don't add anything. And we have 1 here. So we need to add up all those numbers. So we get 16 plus 8 plus 1, which adds up to 25. So this is the binary representation for 25. Now let's see how we can convert decimal numbers into binary numbers. Let's proceed by examples. First, we want to convert 75, which is a decimal number, into its binary representation. So when we want to work with binary numbers, it's good that we remember powers of 2, we should write a list of them. We start by 1, which is 2 to the 0, then 2, which is 2 to the 1, then 4, 8, 16, 32, 64, 128. In this case, we don't need to go beyond, because in binary representation, we basically want to know what sum of these base 2 numbers results in the number we have in the decimal system. So since 128 is already greater than 75, we don't need it, and we don't need to continue to next numbers either. So here I'm going to teach you a method called subtraction method, which works in the following way. So for the number we want to convert to binary, we find first the highest number in our list of base 2 numbers, which is just under this number. So here we have 75. The highest number in our list, which is under 75, is 64. We pick 64. So this will actually give us one of our bits or binary digits. We subtract it. So we have 75 minus 64. We obtain 11. So again, we follow this process. So we find in our list the highest number, which is under 11. So we have 8. That is just under 11. So again, we subtract it. 11 minus 8 is 3. So in our list, we again need to find the highest number that is under 3. We have 2 here. We subtract it. 3 minus 2 gives us 1. And we have 1 in our list. So 1 minus 1 is 0. So you see, in our calculations, we have collected a set of base 2 numbers, being 64, 8, 2, and 1, whose sum actually gives us 75. So 75 is equal to 64 plus 8 plus 2 plus 1. And all these numbers are powers of 2. So let's see if we have calculated correctly. 64 plus 8 gives us 72. 72 plus 2 is 74. 74 plus 1 is 75. So this calculation was correct. And these numbers basically tell us which digits in our binary representation should be 1 and the rest would be 0. So our binary representation would be like this. So for 64, we put 1. We don't have neither 32 nor 16, so we put zeros here, but we have 8 because you remember we had 8. We put 1 here. We don't have a 4. We put 0 here, and we have a 2 and we have a 1. So we put 1 in here and here. So this is actually the binary representation of our number, which was 75. Let's see another example. Now we want to convert 142 into binary. So we again write base 2 numbers, 1, 2, 4, 8, until we come to 128. We don't need to go beyond this because we will obtain a number which is higher than 142. So we start here, so we subtract 128. So 142 minus 128 gives us 14. So again, in our list, we need to find the highest number, which is under 14. 16 is not under 14, so we pick 8. 14 minus 8 gives us 6. So which number in our list is the highest number just under 6? We don't have 5, for example, obviously, because it's not a power of 2. So we have 4 here. So we subtract it from 6. 6 minus 4 gives us 2. And we have 2 in our list. So we don't need to go to a smaller number. So we do 2 minus 2 gives us 0. So we always continue our calculations until we reach 0. And remember, there is always a unique representation in any base for your number. So in base 2, we have just a unique representation for any number that you pick. So here, as you see, again, we have collected the list of base 2 numbers that together add up to 142. So again, when we want to write the binary representation, we put 1 in a position that corresponds to 128 and all these other numbers, but in the other positions, we write 0. So you see here, we put 1 here. We don't have 64, nor 32, nor 13, sorry, 16. So we put zeros in here, but we have 8 and 4 and 2. We put 1s here and 0 here. So this is the binary representation for 142. Binary numbers are not as efficient as base 10 numbers or decimal numbers because you see they need more digits. For example, we could represent 142 in decimal system with only 3 digits, but in binary system, we need 8 digits for it. So although binary numbers are not as efficient as base 10, but they are exponentially more efficient than tally marks. But why did the inventors of computers, these smart people, use binary numbers inside computers? Why not base 10 simply? This goes back to the building blocks of computers. So from the second generation, we know that the building blocks of computers were transistors. So transistors work like a switch inside your computer. So they are, when the electricity is applied to them, they are on, and when there is no electricity applied, they are off. So they have basically 2 states, on and off. So imagine we want to count things with the transistors that we have inside our computer. How would we count with the transistors that have 2 states? Because the basic thing that was done even in the first computers was doing the calculations, very simple mathematical calculations. So they needed in the first place to represent numbers in the computers. How about using tally system? In tally system, we would need many transistors for very low numbers. For example, for representing 4, we would need 4 transistors. This is not efficient at all, not practical at all. So what was done instead was to use transistors to show the binary numbers because they fit very well. They have 2 states, on and off. And in binary system, we need 2 different ways of, or 2 different digits, 0 and 1. So they perfectly fit. So using binary system is much more efficient than tally system. So this is why binary systems were used, because even nowadays transistors are still used inside our computers, not as a single transistors, but in forms of VLSIs and ULSIs. Let's compare a little bit the tally system and binary system. If we had 8 transistors, in tally system, we could just be able to count from 0 to 8. Whereas in the binary system, we can count from 0 to 255, because with the first transistor, we can show 0 or 1. The second transistor can show 2, the next one 4, 8, 16, 32, and the 8th transistor can show 128, and when we add up all this together, it gives us 255. Bit stands for binary digit, and a bit is actually 1 transistor. And when 8 transistors are collected together to show a piece of data, they are called a byte, which, as I said before, the 8 bytes or 8 sorry, 8 bits or 8 transistors can count from 0 to 255. So we saw how we can represent numbers inside our computer. But what about other piece of information? For example, how can we do spelling in binary? When we want to use binary numbers to show alphabet, we need to associate each letter to a number. Then we represent that letter in the binary system. But there are different ways to associate numbers to alphabet letters. So then a standard was introduced, which is called ASCII, which stands for American Standard Code Information Interchange. So it basically tells us what number should be associated to which letter. So here you see a table which is called the ASCII table. So here, for example, let's see here. So here we have A, B, C, D, all alphabet letters and all other characters that you might use. For example, you see here every possible character that you can enter with your keyboard. All of them are associated to a decimal number, and then its binary representation is also written beside. Also, its other representations, like its representation in hexadecimal numbers, is also written beside. All these have the same value. They're just different representations. And you see that for capital A, the associated value is different. So here we have 65, whereas small a, which has 97 as its numerical representation. So each time, for example, you write capital A, so somewhere in your computer, the transistors get on and off like this to represent this value, which corresponds to the binary representation of A. So here you see that its decimal value is 65 and its binary representation is like this. So somewhere in your computer, some tiny transistors form this piece of data. But a byte, which is essentially 8 bits, is not enough for all data we want to store in our computers and everything we want to do. For example, imagine computer games, graphics, all the messages, the social media that we're using. We cannot just put all those in 8 bits, which gives us essentially only 255 different cases. So what can we do? So a solution is that we put more transistors together. So for example, instead of just having 1 byte, we can have 2 bytes to represent all the different data that we need. So with 2 bytes, we have a huge improvement. So we go, 2 bytes is essentially 16 bits. So we go from 2 to the 0 to 2 to 15. And when we add up all this together, this gives us over 65,000 different combinations of the transistors that gives us this many different numbers that we can show in a computer that has 2 bytes. So the early machines had just 1 byte or even less, and then in the next improvement, they had 16 bits or 2 bytes using. So they improved a lot. When we work with base 2 or binary numbers in our computer, we often also need to know about hexadecimal numbers or base 16, because you saw the representation of numbers in binary system was too long. We can have a representation in hexadecimal, which is easily convertible to base 2 representation, and it takes much less space. So let's see how it works. Hexadecimal, or hex for short, is actually base 16. So what are the digits that we use in this system? In decimal system, which was base 10, we had the digits 0 to 9 because we just needed to distinguish 10 different values. But here we are using base 16, so we want to have 16 different cases. So 0 to 9 is not enough for us. Beyond that, alphabetical letters were used. So A is used in this numerical system to represent 10, the digit 10. B is used to show 11, C for 12, E for 13, D for 14, and F for 15. Let's see an example. So here we have a number in hexadecimal system, which is A100. So similar to base 2 system, we put the base and then we put its power. So here we have 16 to 0, 16 to 1, 16 to 2, 16 to 3. So this position basically stores the number of ones. In the next position, we write the number of 16s. The next one, the number of 256, and so on. And you remember, A shows value 10, a digit that has value 10. So let's see what is the decimal representation of this number. So we need to multiply each digit by by the value of its position. So here A is basically 10, as we had seen before. And then we need to multiply it by 6 into 3, which gives us 4096. And then we need to add it to the next value, which is in this case 1 times 256. This position, I mean. And in the next two positions, we have 0. Sorry. So A100 in hexadecimal representation is equivalent to 41,216 in decimal representation. It is easy to convert from hexadecimal or hex to binary. Each digit in hex can be represented by 4 binary digits because you see binary is base 2, hex is base 16. 16 is 2 to the 4. So each digit here corresponds to 4 digits there. So let's see a small example. We have A9 in hexadecimal representation. We want to see what would be its binary representation. We consider its digits separately and we convert them one by one. So let's see what is the representation of A in binary. A was 10, if you remember from the previous slide. When we want to show 10 in base 2, 10 is easily the sum of 8 and 2. So in these positions, we put 1, you see here. And in the two other positions, we put 0. And you remember, we show each digit in hex with 4 digits in binary. So here we have used our 4 bits. So let's see how we can convert 9 to binary. So 9 in hex can be represented as the sum of 8 and 1. So its binary representation is 1, 0, 0, 1. We put these two together. So the representation of A9 in the hexadecimal would be 1010 taken from here and 1001 taken from here. So now let's see if we did our calculations correct. Is A9 in hex really equivalent to 10101001 in binary? So we need to sum up all these base 2 numbers that correspond to this binary representation to see what we get. So I have written it in this table. So we start adding. So we have 1 here, and then we have 8 here, and in the here we have 0, so we don't need to add anything. In the next position, we have 32. And in the next position, we have 128. And when we add up these together, we obtain 169. And when we convert this value also to decimal, we have, so A represents 10. And we need to multiply it by 16 because in the first position, we have 16 to 0. And in the next position, we have 16 to 1, which is 16. And we add it with 9. So again, we get 169. So these two numbers are equivalent. So these two representations in hex and binary are correct. They correspond to each other. Let's see a little bit how we can do arithmetic operations in binary representation. So let's see some basic cases. When we have 0 plus 0 bits, it gives us 0. When we have 0 plus 1, it gives us 1. And 1 plus 1 gives us 2, but we cannot write 2 directly in binary because we have just zeros and ones. So we write 0 here, and we have a carry of 1, and we write 1 here. Why do we have a carry of 1 and not 2? Because each time we go from a digit to the next digit, it is multiplied by 2. So we needed a 2 here, which we couldn't represent. We need to go to the next place. That place already is showing 2. So we need to divide the 2 that we had here by 2, so we get basically 1. So 1 plus 1, is equal to 2. The binary representation of 2, is also 1, 0. So we use these basic cases for binary additions with as many bits as we have. So let's see an example. So here we want to sum 0, 1, 1 with 1, 1, 0. We start from the right most bits as if we would do addition in base 10. So we always start from the right most digits. So 1 plus 0 is 1. Then we move on to the next bits. 1 plus 1 is 2. So we learned that it will give us a carry. We put 0 here and a carry that goes to the next position. And again, here we have 1 plus 1, which gives us a 0 and a carry that we move it down. So let's see if we have calculated correctly. In the first row, we had 1, 1, which is the binary representation for 3. In the next row, we have 1, 1, 0, which is the binary representation for, here we have 2, here we have 4. So this is basically 6. 6 plus 3 gives us 9. Let's see if this value that we have obtained here is also 9. So in the first position, this 1 shows 1. In the next position, we have 2, 4, 8. These are 0. So here we have 8 plus 1, which gives us 9. So our calculation was correct. Let's see another example. So we want to sum up these two values. 1 plus 1, gives us a 0 and a carry. Here we have 3 ones. 1 plus 1 plus 1 is 3. How can we write it down here? So 3 in binary representation would be 1, 1. So we write down 1, and we also will have a carry. So we have a 1 here and a 1 here. And again, 1 plus 1 would be 2, which would be translated in here as 0 and the carry. And again, we have 1 plus 1, so we write it as 0 and the carry. So now let's see if we have done correctly, if we have performed our calculation correctly. So in the first row, we have the binary representation of 7, because we have 1 plus 2 plus 4, which gives us 7. And in the next row, we have 1 plus 2 plus 8, which gives us 11. So our result should be 18. Let's see if we have obtained 18 here. So this is 2, and this is 4, this is 8, this is 16. So we have 16 plus 2. This gives us 18. So we have calculated correctly. So now let's see how binary subtraction is performed. Again, we need to first see some basic cases. So 0 minus 0 is 0. It is easy. But 1 minus 0 is 1. 1 minus 1 is 0. But how about this case? We have a 0 here that we want to subtract by 1. We cannot write minus 1 here. So what we do in this case is that we borrow from the next digit. So this becomes a 0, and this gives us a 2 in this position, because remember, each digit is twice more powerful than its previous digit. So here, if we remove this 1 from here, it gives us a 2 in the first position. So 2 minus 1 will be 1, and we write it down here, and this 0 is also moved down here. So now let's see with more examples. So now we want to subtract 1, 0, 0 by 1, 0. We start from the rightmost bits. 0 minus 0 is simply 0. In the next place, we have 0 minus 1. So here we need to borrow. And we have a 1 in the next position. So we are lucky. We just borrow from that. So this 1 becomes 0. And we get a 2 here. It's like base 10 when we borrow. It's the same logic, just that the base has been different here. So 2 minus 1 gives us 1. And 0 is simply transferred down, moved down. So we have 0, 1, 0. Let's see whether or not we have calculated correctly. This first number is the binary representation of 4, because you remember this place shows 1, this is 2, and this is 4. So this is 4. And the second number is the binary representation of 2. So we know 4 minus 2 is 2. And we have here obtained 1, 0, which is the binary representation of 2. So our calculation was correct. Now let's see another example. So here we want to subtract 39 by 25. So I have written their binary representation. You can stop the video and write their binary representation for your own and then continue. So we start from the rightmost bits. 1 minus 1 is 0. 1 minus 0 is 1. 1 minus 0 is 1. Here we cannot do 0 minus 1. We need to borrow, but the next digit is also 0. So we need to go to the next one. So this becomes 0 and gives us a 2. But again, we need to borrow from that to give us 2 in this position. So this becomes 1 and gives us a 2 here. So 2 minus 1 is 1. And 1 minus 1 is 0. And 0 minus 0 is 0. 0 minus 0 is 0. So let's see if we have calculated correctly. So our numbers were 39 minus 25. So we expect that the result would be 14. In here, we have the representation, which is equal to the sum of 2 plus 4 plus 8. 2 plus 4 gives us 6. 6 plus 8 is 14. So our calculation was correct. So far we have seen how positive numbers are represented in binary system, but what about negative numbers? How can we represent negative numbers in binary system. So there are two methods to show negative numbers. The first one is called sign magnitude. The other one is called 2's complement. In the sign magnitude, we dedicate the leftmost bit or the highest value bit to sign. When it is 0, we consider the number to be positive, and when it is 1, the number is negative. So let's see an example. So we have 7, which is represented in binary as 111. And here, imagine we have 5 digits. So we put 0 in the 2 higher positions. Now, if we want to show -7 using sign magnitude, we would need to change the leftmost bit or the highest bit to 1, and the rest stays the same. So let's see how we can work with these numbers. For example, we are interested in doing arithmetic. What would be the sum of 7 plus -7? Would it be 0? If we do our calculations here and we add up these two values, we see that actually our result is not 0. So we cannot do arithmetic operations easily in this method. So it is not a very interesting method. So another approach is used in which arithmetic operations are easily possible, and it is called 2's complement method. In 2's complement method, I should first introduce 1's complement. 1's complement is very simple. 1's complement of a number is simply obtained by flipping all its bits or inversing all its bits. So let's see here we have 7, which is represented by 5 bits as 0, 0, 1, 1, 1. And its 1's complement is simply obtained by inversing all its bits. So we have 1, 1, 0, 0, 0. So this was the first step. In 2's complement, we need to first perform 1's complement of the number, and then we need to add it to 1. Then we obtain the 2's complement, and 2's complement is actually 2's complement of a number is actually its a negative representation. So let's again see our example with 7. So 7 was represented by 0, 0, 1, 1, 1. And then we we want to negate it. So first we need to perform 1's complement. So we simply flip its bits, and then we add it with 1. We add the 1 to the lowest bit, of course. So we will obtain 1, 1, 0, 0, 1. This is actually the representation for -7. So now let's see if our arithmetic operations would work in this case. So we want to see, before we go there, let's see what is the value here. So you remember in base 2, we say this shows the value 1, this is 2, this is 4, this is 8, and this is 16. But here, because we are using 2's complement, this last bit is not anymore 16. It is rather -16, because we had decided that the leftmost digit shows the sign. So here it's like it is treated at -1. So this will give us -16, and this next bit gives us 8. The rest are positive. Only the leftmost bit is treated as a negative value. So and we have a 1 here. So we will get -16 plus 8 plus 1, which gives us -7. So we saw that this is giving us -7. Now let's see simple arithmetic. For example, we want to sum 7 and -7. What do we get? So let's do it here. So this is the representation for 7. And in the next row, we have -7. So 1 plus 1 becomes 2, which has a 0 here and a carry in the next digit. Again, we have 1 plus 1. So we have a 0 here, a carry, 1 plus 1, 0 carry, 1 plus 1, 0 carry, 1 plus 1, 0 carry. And we discard the last carry. So we have obtained 0. And so the 2's complement method works with arithmetic, and we can easily do addition, subtraction. So when we want to do addition in this system, we simply have to find the 2's complement of the negative operands. For example, you saw we first calculated the 2's complement of minus 7. And then what we obtain, we simply add up together like the previous method we had for positive numbers. It's no difference. When we want to do subtraction in this method, we negate the second operand. We have to obtain its 2's complement basically. And then we add up the 2 numbers together and discard the carry. Let's see an example. So we want to do this subtraction. We want to do 39 minus 25. In the straightforward method, which was the previous method I had shown you for positive numbers, we simply write them and follow the steps for subtraction. But in the 2's complement method, what we do is that we add up 39 with 2's complement of 25. So this is logically equivalent to the previous operation. And we expect it to give us the same result. So here we add the binary representation of 39 as in the previous case. But in this time, we add up 2 numbers as opposed to the previous method, which we subtracted. But our second operand is different here. In this case, we write the 2's complement of 25. Let's practice a little bit to see what is the 2's complement of 25. So here it's the representation for 25, the positive 25. For 2's complement, we have to reverse its bits and sum it with 1. So when we reverse these bits, we get 1, 1, 0, 0, 1, 1, and we will have a 0. But then we need to add a 1 to it, so we will get a 1 here. And when we add up these 2 numbers together, we obtain the same results. I leave it as an exercise for you. So we discussed how we can represent binary numbers in the computers and how we can represent negative binary numbers and how simple arithmetic is done. Please feel free to ask your questions either via the forum on Studium or use the mailing system in Studium to contact the teaching assistants. Thank you very much.